Welcome to all students in our ROSE project conducted by Rayat Shikshan Sanstha Satara. I am Mrs. Shinde SR from Sadguru Gadge Maharaj College, Karad. Today we are going to study the topic coordination compounds. In last lecture we study about the some terms used in the coordination compound. Today in second lecture we study about the Werner theory of coordination complex, classification of complexes, and IUPAC nomenclature of coordination compounds. Now start first Werner theory of coordination compounds. There are the four postulates of the Werner theory. See one by one. The first postulates of Werner theory is, unlike metal salts, the metal in a complex possesses two types of valencies, primary valency and secondary valency. That means first postulate is the in metal complex there are the two valencies, primary valency and secondary valency, in which the primary valency is the ionizable and secondary valency is the non-ionizable. The second postulate is, the ionizable sphere consists of entities which satisfy primary valency of metal, and the primary valencies are generally satisfied by anions. That means the primary valency is the ionizable valency, ionizable. That's why these valencies are satisfied by the anions. Then third postulate is the secondary coordination sphere consists of entities which satisfy the secondary valency and are non-ionizable. The secondary valencies of metal ion are fixed. Also, the number of secondary valency is equal to the coordination number. It is very important. The secondary coordination spheres, there are the two spheres, primary sphere and secondary sphere. The primary, it is also called as the valencies, primary valency and secondary valency. The primary valency is the ionizable and secondary valency is the non-ionizable. And the secondary valencies of metal ion is fixed and it is the equal to the coordination number. That means the compounds which having the secondary valencies is it's the coordination number. The secondary valencies have fixed spatial arrangement around the central metal ion. Last postulates given by this Werner theory is the secondary valencies have fixed spatial arrangement around the metal ion. That means there is the fixed arrangement of these secondary valencies, and due to these secondary valencies the metal complex have the different geometrical shape. They have the different geometrical arrangement because they are fixed spatial arrangement. If the Cn is equal to 6, that means that compound having the secondary valency is 6. And if the secondary valency is 6, then its coordination number is 6 and it have the fixed spatial arrangement which is the octahedral structure. And if coordination number is 4, that means secondary valency is 4, which is the non-ionizable. And if coordination number is 4, then its arrangement or its geometry is the tetrahedral or square planar structure. That means according to their coordination number, they have fixed structures. And now see the for example, COCH3 6 Cl3. This is the example of the complex, coordination complex. It has the two spheres of attraction. It has the two spheres of the attraction. That means there are the two spheres, primary sphere and secondary sphere. It is also called as the primary valencies or secondary valency. Now see this, in this example, the CO, that means cobalt, is the central metal ion, and it is surrounded by these the 6 NH3 groups, which are called as the secondary valencies. That means central metal ion is satisfied by these 6 amine groups, and these are the, there are the 6 secondary valencies are 6, therefore its coordination number is also 6. And this Cl3, it is the primary sphere, which is the ionizable, and this secondary sphere is called as the coordination sphere. This secondary valencies is called as the coordination sphere. That means this complex having the two valencies, secondary valencies and these primary valencies. The primary valency is the ionizable and the secondary valencies are the non-ionizable. Secondary valencies is enclosed in the square bracket. It is also called as the coordination sphere, and primary valency is right in the after the square bracket, and it is the ionizable, and it is the non-ionizable. When this compound is reacts with the silver nitrate, then it gives the 3 molecules of the silver chlorides. When this compound is treated with the silver nitrate, then it gives the 3 molecules of the silver chloride, because there is the presence of the 3 chloride ions, and which is reacts with the AgNO3, because this primary valencies are the ionizable, and therefore it gives the 3 molecules of the silver chlorides. In this way, we observe which groups are present in the primary valencies and which groups are present in the secondary valencies. In this way, Werner theory gives the 4 postulates. Now see the classification of complexes. The classification of complexes on the basis of types of ligands. We studied in last lecture the types of ligands. These types of ligands are the monodentate, polydentate and ambidentate ligands. And according to these types of ligands, these complexes are classified as homoleptic complex. It classified as homoleptic complex. Homo means same. That means in this complex there are the only one type of the ligands present. That means the metal ion surrounded by only one type of the ligands. That types of complexes are called as the homoleptic complex. For example, CO NH3 3 plus. That means in this example, this is the central metal ion, and these NH3 groups, there are the 6 NH3 groups. These are the ligands. There is the only one type of the ligands. Therefore, this complex is the homoleptic complex. Then second type is the heteroleptic complex. In heteroleptic complex, that means the ligands are different. Hetero means different. That means the metal ion surrounded by more than one type of the ligands is called as the heteroleptic complexes. For example, CO NH3 4 Cl2. In this example, the central metal ion is the cobalt, and it is surrounded by the 4 amine groups and 2 chloride ions. This central metal ion is surrounded by 4 amine groups and 2 chlorine atoms. There are the different types of these are the different types of ligands, and therefore this type of the complexes is called as the heteroleptic complexes. In this way, according to the types of ligands, they are classified as homoleptic, homoleptic complex and heteroleptic complex. Homoleptic complex containing only one type of ligands, and heteroleptic complex containing different types of the ligands. Now, the classification on the basis of charge on complex. We studied in last lecture the charge. Now, they are classified as cationic sphere complexes. We know the coordination compounds containing counter ion and coordination sphere. And on the charges on this coordination sphere, these complexes are classified as cationic sphere complexes. In this, the coordination sphere having the positively charged. For example, in this example, ZnNH34, this is the coordination sphere which is enclosed in the square bracket and it having the positive charge. That means this coordination sphere having the positively charged, and hence it is the cationic sphere complexes. In this second example, CONH35Cl, and this is SO4. In this example, this SO4 is the ionizable. It is the primary valency and it is the secondary valency. And this complex containing this coordination sphere having positive charge and SO4 having the negative charge. Therefore, this complex is the cationic sphere complexes. That means the complexes which having positively charged coordination spheres are called as the cationic sphere complexes. Then anionic sphere complexes. These anionic sphere complexes having the negatively charged coordination sphere. In this example, here K3FeCN6. This is the coordination sphere which is enclosed in this square bracket we studied. Then this sphere having the negative charge because this K counter ion K, it having the positive charge, and this coordination sphere having the negative charge because this coordination compound on dissociation gives the two ions, complex ion and counter ion. This complex ion having the negative charge. Therefore, it under the anionic sphere complexes. Also, this example NiCN4 having 2 minus, that means the charge having negatively charged. And negatively charged complex coordination sphere undergoes in the anionic sphere complexes. Now see the third type, neutral sphere complexes. It does not having cationic or anionic sphere. That means the coordination sphere is the neutral. For example, see the platinum NH3 twice Cl2. In this example, this coordination sphere does not having any charge. Therefore, it under the neutral sphere complexes. Also, this example in NiCO4, it does not having the any charge. Therefore, it is neutral sphere complexes. In this way, on the basis of charge, the complexes are classified into three types: cationic sphere complexes, which having the coordination sphere positively charged; then anionic sphere complexes, which having the negative charge coordination sphere; and neutral sphere complexes, in which does not having the cationic or anionic sphere. Now see the example. They are classified the complex as homoleptic or heteroleptic. There are some examples given here and we classify them. It is the homoleptic or heteroleptic. In this example, see in this coordination sphere, there are the two types of the ligands, NH3 and Cl. Therefore, two different ligands. Therefore, this compound is the heteroleptic complex. In this example, there are also these two different ligands. Therefore, it is also heteroleptic ligands. In this complex, it is also having the three different ligands. Therefore, it is heteroleptic complex. And in this example, there is only one type of the ligands. Therefore, it is the homoleptic ligands. Also, now see the examples of cationic, anionic and neutral complexes. See here in this example Na plus and this coordination pair having the negative charge. Therefore, it is anionic complexes. In this example also, here the Cl having the negative charge. Therefore, this coordination sphere having the positive charge, and hence this compound is the cationic complexes. CrCO6, this is the neutral compound. There is no any charge. Therefore, it is neutral compound. In this example, this is the coordination sphere. Here, charge is the negative charge. It having the negative charge. Therefore, this compound is the anionic compounds. And in last example, these compounds does not have any charge. Therefore, it is neutral complex. In this way, we can classify the complexes as heteroleptic and homoleptic or cationic or anionic or neutral complexes. Now see the IUPAC nomenclature of coordination compound. In this IUPAC nomenclature, we understand and remember the rules. Now see the one by one rule. The first rule in the naming of complex, ion or neutral molecule, name the ligands first and then the metal. The first rule is if we give the name of this complex ion, then first write the name of the ligands and then metal. The name of anionic ligands are obtained by changing the ending IDE to O and ATE to ATO. This is the rule. Means we know that the coordination sphere, anionic, cationic and neutral. If there is the anionic ligands, then the anionic ligands, the ending of this IDE is O and ATE is the ATO. We see in next slide. Now the third rule is the name of complex is one single word. The name of complex is right in the single word. There must not be any space between different ligand names as well as between ligand's name and the name of the metal. That means the whole number is right in the single word. No any space between the name of ligand and name of the metal. Then after the name of the metal, write its oxidation state in Roman number. After the name of the metal, write its oxidation state in Roman number. That means in the naming of the coordination compound, write the first name of the ligands, then name of the metal ion, and then write the oxidation state in the Roman number. And all these name write in the single word. Now see the next rule. If a complex has more than one ligands of the same type, the number is indicated with prefixes di, tri, tetra, penta, hexa, and so on. We know if there are same number of the ligands, if there are the two same number of the ligands, then write the di. If there are the three numbers are same, three number of ligands are same, then it write as the tri. In this way, we denoted as di, tri, tetra, penta, hexa, and so on. Now see the next rule. For the complex having more than one type of ligands, that means heteroleptic complexes. In heteroleptic complexes, there are the more than one type of the ligands. They are written in an alphabetical order. These are written in the alphabetical order. If the name of ligand itself contains numerical prefix, then display number by prefixes with bis. See in this rule, That means the ligands having the numerical prefix. For example, ethylene diamine. There is the numerical prefix. Therefore, in this type of the name of the ligands, we write the number of prefixes with bis for 2, tris for 3, tetrakis for 4, and so on. In this way, that means if there is the numerical numbers are double, then use the bis, tris, tetrakis, and so on. The metal in cationic or neutral complex is specified by its usual name, while in the anionic complex, the name of metal ends with ATE. In this rule, the metals, if metals are cationic or neutral, metals are cationic or neutral complex. If there is the metals or complexes are cationic or neutral, then it's specified by its usual name. That's use the name of that metal ion. But the complex is the anionic, then the metal ends with the AT. Now see the name of the ligands. The anionic ligands, Br minus bromide. It's in our last rule we know that the IDE from this anionic ligand is replaced by the O. That means the bromide is in IUPAC system, it is the bromo. Chlorides, it is chloro. Fluorides, fluoro. Iodide, iodo. Cyanides, IDE is replaced by O, cyano. Then SO4 2 minus sulfate, sulfato. Then nitrate, nitrato. Then carbonate, CO3 2 minus, carbonate, ATE. In anionic ligands, ATE, the last is replaced by O, carbanato. Then hydroxide, OH minus, hydroxo. Oxalate ion, then oxalato. Nitrite, these two are the ambidentate ligands. That means nitrite when coordinated from nitrogen, it is called as the nitro, and when it is coordinated from oxygen atom, then it is nitrite, nitrito. Then this thiocyanate, it is also by the ambidentate ligands. When it is coordinated from sulfur, then it is called as the thiocyanato. ATE is replaced by ATO. Then when it is coordinated from nitrogen atom, then it is called as the isothiocyanato. Then neutral ligands, the NH3 ammonia in IUPAC system, it is named as the amines. CO carbon monoxide, carbonyl. Then neutral ligands, H2O, water, it is in IUPAC system used as the aqua. Ethylene diamine, it is the ion, it is used in the IUPAC name ethylene diamine. In this way, the anionic and neutral ligands, the name used in the IUPAC name. We understand and we remember all these names for the naming of the IUPAC name of the coordination complexes. Now, in some metals, they are in IUPAC system. The aluminium, Al, it is the aluminate. We studied the rule when the metal in anionic complexes, then it is used here ATE. Then cobalt, cobaltate. Gold, Au, urate. Manganese, manganate. Platinum, platinate. Chromium, chromate. Copper, cuprate. Iron, iron, it is used as the ferrate. It is the Latin word. Then nickel, nickelate. Zinc, zincate. That means these abbreviations are used when the coordination complex is anionic complex. Then use the metal ion, the last ATE. In this way, we remember this chart. Now see some examples for cationic complexes. In cationic complexes, after the naming of ligands, name the central metal. If the complex ion is a cation, the metal is named same as the element. Cationic complex, then the metal ion used as its own name. For example, if there is the metal ion CO, cobalt, in a complex is the cation, then it is used as a cobalt. Platinum is called as the platinum because this complex is the cationic complexes. For example, see here, this is Cr, NH3 thrice, H2O thrice and Cl3. This is the coordination sphere and it is the ionizable sphere. In this coordination sphere, this is the central metal ion and these are the ligands. There are the two types of the ligands, that means amine and water. These are the ligands. There are the 6 numbers are ligands. Then from the IUPAC rule, first we write the name of the ligands. Then there are the 2 different ligands. Then add it is from the alphabetically order, amine and aqua. Then which is the first? The amine. Then first write the name of these ligands. How many amines are there? 3. Therefore tri-amine. Then this water is called as the aqua. In IUPAC name, water's name is the aqua. How many aqua groups there? 3. Therefore tri-aqua. Tri-amine, tri-aqua. Then metal, central metal is the chromium. It is the positive coordination sphere. Therefore, write the name of chromium as it is, chromium. Then write the oxidation state of this metal ion in the bracket. The oxidation state is the 3. Write in the Roman number. And then write this chloride is the ionizable sphere, chloride. Therefore, the name of this compound is the triamine triaqua chromium third chloride. Write in the single word. In this way, next example, platinum is NH35, Cl and Br. In square bracket, it is the coordination sphere, it is the positive charge and it is the ionizable sphere. Then how many amine groups are there? 5 and 1 chlorine atom. Chloro group. Chloride. Then it is abbreviated as chloro. Then first alphabetically. Therefore name of this compound is the pentaamine chloro platinum as it is because it is the cationic complex. Then oxidation number 4 and bromide. In this way we give the name for the cationic complexes. Now see for anionic complex. If the complex ion is an anion, the name of the metal ends with the suffix ate. In last rule up, you know that in anionic complexes the metal ion is suffix with the ate. For example, CO, cobalt in the complex anion is called as the cobaltate. Platinum is called as the platinate in only anionic complex. For some metals, the Latin names are used in the complex anions. For example, Fe is called as the ferrate, not ironate. Fe is the iron, but it is known as the ferrate. For example, K4 FeCl6. This coordination sphere is the negative charge. Therefore, it is anionic complex. First, we know that this complex is the anionic, cationic or neutral and then use the IUPAC rules. This complex is the anionic complex. Then first write the positive charge, potassium. Write the first potassium. Then write the name of the ligand. How many ligands are there? 6. Therefore, write here hexacyanoferrate and then write the oxidation number. In this way, in this example, the sodium tetrachloronickelate and the oxidation number is the second. In this way, we give the IUPAC name for the anionic complex. Now see some examples. The first, anionic complexes. These complexes are the anionic. That means they having the negative charge. If the anionic, then this central metal ion is attached to the ATE. Then how many ligands are there? 4. Which ligands? Cyanide. These are the negative ligands. Therefore, write the tetracyanonickelate second ion. In this way. Then in second, this cobalt having this the oxalato. This is the oxalato. Then the name of this compound is the trioxalato cobaltate 3 ion. Then FeCN6 4 minus hexacyanoferrate second ion. The next compound is the tetracyanonickelate second. This is the oxidation state. We know that in the IUPAC system, write the first name of the ligands, then metal, ion, and then the oxidation state in the Roman number. Then compounds containing complex anion and metal cations. That means in this type of the complexes, how it is IUPAC name. See here, first write this positive metal cation. Which is the metal cation in this complex? The sodium. First write the sodium. Then this is the positive coordination sphere. And therefore, in this type of the complexes, write the name of this metal ion as it is. Then, in these complexes, this coordination sphere is the negative charge because this counter ion is the positive charge. Then use this metal ion as with suffix ATE. The name of this complex is the sodium hexanitrocobaltate 3. In this way, in this example, the potassium, the first metal cation is the potassium. Then write the name of the ligands. There is the potassium trioxalato and aluminium. Write the ATE, aluminate. The name of this complex is the potassium trioxalato aluminate 3. Then this compound, the sodium, there is the ligands are fluoro. How many? 6. Therefore, name of this compound is the sodium hexafluoroaluminate and 3. Oxidation state is the 3. Mention the oxidation state of this central metal ion. Then this is also cation, sodium. Then this is the oxalato. How many? 3. Tri. 3 is abbreviated as tri. Then name of this complex is the sodium trioxalatoferrate and write the oxidation state of this complex. Now if the complexes are cationic, then how it is? Right. For example, there is the ligands. How many? 4. Which ligands? Amine. Then name of this complex is the tetraamine copper. Name of this metal ion as it is, copper. Then write the oxidation number, second. In this way, in the next example, there are the 2 ligands. One is the aqua and this is the thiocyanato. But in thiocyanato, it is attached from this nitrogen. Therefore, this group is the isothiocyanato. Then write the alphabetical name. First write the aqua. Then how many groups are there? 5. Then penta, aqua, isocyanato, iron. because this is the cationic complex. Therefore, write the name of this Fe is the iron, and then write the oxidation number. Now see the in next example, platinum En12. En is the ethylene diamine. If the ligands having the numerical, then use the bis, because this En number, how many groups are these? Two groups are. Two groups of ethylene diamine and two groups of the thiocyanate. That's this ethylene diamine. In the name of this ligand, there is a di. That's mean there is also numericals. There is also two numericals. Therefore, if in this type of the example, use the bis for 2. Then what is the name of this compound? Bis. Write in the bracket ethylene diamine. That means this ethylene diamines in the 2 times. Bis, ethylene diamine, dithiocyanate platinum. And oxidation number is the 4. In this way, we give the IUPAC name as it is. Then next complex is the CONH3,5Cl. Here also 2 types of the ligands. Then write the alphabetical name. Then how many amines groups are there? 5. Therefore, name of this compound is the pentaamine chlorocobalt ion. In this way, we give the different types of the complexes. Then now see the next examples, cationic complexes. In these cationic complexes, there is this is the positively charged sphere, it is the negative. Then if negative, then write it the last. If positive cation, write the first. Therefore, the name of this complex is the tetraamine dibromo platinum. Then write the its oxidation state and then bromide. In this way. Also, name of this complex is the how many amines group are there? 5. The name of this group's complex is the pentaamine carbonato cobalt chloride, because there is the ionizable sphere is the chloride, negative group. Then in next example, pentaamine, there are the aqua and amine. First is the amine, alphabetically order. Pentaamine, then aqua, cobalt, the oxidation state is 3rd, iodide. In this way. Then this AgNH3 twice NO3. How many NH3 groups are there? 2. Therefore, diamine silver, the oxidation state is the 1, and nitrate. NO3 is the nitrate. Then neutral complexes. In neutral complexes, the first write the same as write the first name of the ligands and then write the name of the metal and then oxidation state. In this example, there are the 2 ligands. How many? 3 amines, triamine, trinitro, cobalt, 3. Then FeCO5. There is the carbon monoxide, is called as the carbonyl group. Then how many? 5. Therefore, name of this compound is the pentacarbonyl iron. The oxidation state is here 0. In this example, there is the 3 amines groups and 3 thiocyanate group. Then alphabetically, the name of this compound is the triamine trithiocyanate rhodium. The oxidation state is the 3. The next complex NiCO4. 4. There are carbonyl groups are present. Therefore, name of this compound is the tetracarbonyl nickel. Oxidation state is the 0. In this way, we give the different names to the coordination complex. First, we know that first this compound is the anionic or cationic or then neutral. And if there is the cationic or neutral, then metal ion use as its own name. But if the complexes is the anionic, then use the ATE as a suffix. In this way, in the IUPAC nomenclature of the coordination compounds, first remember that first write the name of the ligands, then name of the metal, and then write the oxidation number in the Roman in bracket. In this way, we try to understand and remember all these groups. Okay, thank you.